Welcome to Lecture 7 of Advanced Microeconomics with me, Dr. Craig Webb. In today's lecture, we will be looking at auctions. We'll give a short but detailed introduction into auction theory. Now, auctions have been around for a very long time and used since antiquity. And they're very useful in particular for price discovery. Now, for buying everyday items, shampoo and so on, it would be very inconvenient to go to an auction and bid, and so markets tend to work better. But where we have items, rare items, perhaps pieces of art, where the market and the forces of supply and demand are not able to kind of identify the appropriate price, auctions are very useful. In this lecture, we're going to study two types of auctions, the first price sealed bid auction and the second price sealed bid auction, and we'll calculate expected revenues for these different auction formats and touch upon the revenue equivalence theorem. Now, before we get started with studying auctions, we're going to need to develop some more technical tools, something that's called order statistics. So about the first half hour of this lecture, we'll be developing the idea of order statistics so that we can use these tools when we study auctions, which we're going to model as games of incomplete information. Lots to do, so let's get started. So let's begin our discussion of order statistics by looking at a simple example. So let's consider three random variables. So I'm looking at the outcome of rolling 3 dice. Clearly, we know how to describe the distribution of these random variables, each being a uniform, discrete random variable. So in particular, the outcome of each of these dice are independent of each other, and they share the same distribution. They each assign equal probability to the 6 possible numbers. So if I wanted to calculate, for example, the probability that if I just look at one of the dice and say, well, what's the probability that that particular dice, when I roll it, gives a number that is less than or equal to 4, we know how to calculate this type of thing. We simply add up the probability that is equal to 1, 2, 3, and 4. Summing these up, we can see that the probability that dice 1 has a number which is less than or equal to 4 is 2/3. Now, I've only calculated the probability of one particular dice having its value less than or equal to 4, but we might want to calculate the probability that every one of the dice, when they are rolled, have an outcome less than or equal to 4, for example. Being able to calculate such probabilities is going to be very useful when we're looking at auction theory. You might imagine 3 people walk into the room and they each have some random value for an object, and we want to know, well, what's the probability that they each have a value less than or equal to a certain number? This is the kind of thing we would need to know in order to calculate expected revenues from auctions and so on. So to make this kind of calculation, we're going to look at something called the first order statistic. So what is the first order statistic? Essentially, in this case, I'm looking at 3 random variables. So I could look at a sample. So I could say, well, what values do these random variables take? And then look at the maximum of those values. We call this the first order statistic for that particular sample. So the first order statistic would be capital X subscript 1 in brackets. We normally denote the 1 in brackets when we're talking about order statistics, would simply be the maximum of X1, X2, and X3, our 3 dice in this example. Note that in some textbooks, when they say first order statistic, they're talking about the minimum, and what we call the first order statistic would be called the third order statistic. So just keep an eye on this if you read different textbooks. So let's have a look at the behavior of this first order statistic. If I roll the dice once, then the first time I'm getting values 2, 1, and 1. And so the first order statistic for this sample is equal to 2, the highest number. Rolling the dice again gives another sample from our 3 random variables, and now we have values 5, 3, and 6, and so the first order statistic for this sample is equal to 6. Finally, rolling the dice again, we get a new sample with values 4, 6, and 2, and so the first order statistic for this final sample is again equal to 6, the maximum of 4, 6, and 2. Now, if you recall, we calculated the probability that each of our independent random variables, each of these 3 dice, takes a value less than or equal to 4, and we calculated this to be 2/3. Now, looking at the sample here, our probability has done a fantastic job of describing what actually happened. So x1 was less than or equal to 4 on 2 out of 3 occasions, and so was x2, and so on was x3. So I couldn't have planned this better. That need not have happened, but it's what we should expect to happen. Looking at the order statistic, however, it's greater than 4 most of the time in this example. So only on one occasion is it less than or equal to 4. So what can we say about the probabilities or the distribution function regarding the first order statistic? How do we calculate its distribution function? So let's do that now. The distribution of the first order statistic, if I want to know the probability that our first order statistic is less than or equal to 4, well, what I'm requiring is that every one of the dice, each of the dice, is less than or equal to 4. So there are 3 independent things that need to happen. So I would multiply the probability that x1 is less than or equal to 4 by the probability that x2 is less than or equal to 4, and times that by the probability that x3 is less than or equal to 4. Clearly, these are independent random variables, and so I can multiply their probabilities to find out this overall probability that the highest of their values is less than or equal to 4. Because the dice each have identical distributions, I know that the probability that each of them takes a value less than or equal to 4 is equal to 2/3, and so I can multiply this by itself 3 times and get 2/3 to the power 3, or 8/27, is the probability that our first order statistic is less than or equal to 4. 8/27 is just less than a third. So that's pretty much what we saw. We saw that a third of the time our first order statistic was below 4, and the rest of the time it was above 4. Using exactly the same ideas, we could calculate more generally the distribution function by saying what's the probability that our first order statistic takes a value less than or equal to any particular small x, where x is either 1, 2, 3, 4, 5, or 6. And if you do the calculation, you'll find that we simply take x over 6, so we're adding up 1 over 6 x times for each of the random variables, and then we take that to the power 3 because there are 3 independent random variables in this case. So there we've fully described the distribution of our first order statistic for the case of a discrete uniform random variable. Now, to do auction theory, we're going to work with continuous random variables. So let's go on paper now and figure out how to do the first order statistic, how to calculate its distribution function and its density function for the case of a continuous uniform random variable. Okay, so let's talk about the first order statistic when we're dealing with a number of random variables that are continuous random variables. We're going to simplify this and deal with uniform random variables. Okay, so let's consider I'll use the notation from the lecture notes. So we'll be thinking about some random values that individuals might have for an object. So I'm going to do v1 tilde up to vn tilde as n random variables, which we're going to think of as our individuals' random values for an object that's going into an auction. We're going to model auctions as games of incomplete information. We'll go into the details next, but let's just get the technical results out of the way first. So what are we going to assume? Well, we're going to assume, if we remember the idea of a distribution function, which we covered, I think, in lecture 3. So we typically denote this, let's say fi, so I'll pick I as one of these random variables and say, what does the distribution tell us? Well, if I pick a value v, so that's just a number, then the distribution function is telling me the probability that our random variable v tilde I is less than or equal to this value v. Okay, so we've seen that before. Now, what are we going to assume about these random variables? Well, we're going to assume that they have identical distributions. This doesn't mean that every individual will have the same value. It just means that they have the same distribution of values. So we're going to assume that the distributions are identical. F1 up to Fn are all the same, so we'll just denote it as capital F. Okay. We're going to assume that they're independent. So let's put this higher up. Independent for now. Later, when you study auction theory, or each of these assumptions gets examined, but in this course we'll be looking at independent random variables with identical distributions. And to make it even more simple, we're going to assume that these are uniform random variables. Okay, and we've seen the uniform distribution before. There's a video in the lecture 3 material, the material on adverse selection, which just says that the distribution function looks like this. So what's the probability that one of these random variables takes a value less than or equal to v is simply equal to v itself. Okay, so we've seen this before, and we'll assume they're uniform and that the support, so what is the interval of values that they might take? We'll just say it's 0 to 1. Okay, so all of this can be changed, but this is a good starting point. We have n random values. Each of them are independent, and they take values from the interval 0 to 1, and they are uniformly distributed on that interval. Okay, so that's a very basic setup. Just remember one other idea, which I think we came across, the idea of a density function. Okay, which we typically denote small f. Okay, and you can just remember that you find the density function by differentiating the distribution function. Okay, what would that mean? I mean, essentially, it's describing the probability within a small area. So let me just give you. If we remember what a derivative is, it's essentially saying what would be the probability that our random variable v takes a value between, our random variable v tilde takes a value between v and then v plus epsilon. Okay, so that's the probability it takes a value in some small interval, and then we divide by epsilon and then take the limit of that epsilon going to 0. Okay, so this is formally what a density function is telling us, which is essentially the derivative of the the distribution function. Okay, so knowing what they are is going to help, but really knowing how to use them. We use density functions to calculate expected values, and that's why we need to know them. We use them also to calculate, once you calculate expected values, you can calculate variances and other relevant summary statistics. So that's why we'll need to know them. Okay, but we're going to talk about the first order statistic. So if we remember what that was, let's denote it v tilde, and then I put the 1 in brackets. That's just a standard way of denoting the first order statistic. And essentially it's the maximum of these values. That is, you take a sample from n observations of these random variables, you look at the highest value, that's the first order statistic. And you can think of the first order statistic itself as a random variable. So we want to calculate, in order to understand it, we need to know what's its distribution function. So we'll denote that f1. And what's its density function? So we'll denote that lowercase f1. So once we know these two things, then we'll be able to calculate, for instance, the expected value of our first order statistic. So let's figure out what this thing looks like. Let me get another piece of card. The distribution function of the first order statistic. So what does it mean? So the distribution of the first order statistic calculated at a value v is going to tell me the probability that our first order statistic is less than or equal to v. Okay, so the probability that our first order statistic is less than or equal to v. Now, because our first order statistic is the highest of these n random variables, all I'm asking is that every one of our random variables takes a value less than or equal to v. Okay, if the highest of them is less than or equal to v, then they all need to be. So you could say, well, this is the probability that v tilde 1 is less than or equal to v, and they're independent, so I multiply the probability v2 and so on, all the way up to the probability that v tilde n is less than or equal to v. Okay, so n independent things have to happen. Every random variable has to be less than some value v, and we can calculate the probability by multiplying, because these are independent random variables. And because they have identical distributions, this term here for each of them is simply the distribution function. So it's f of v multiplied by itself n times. So f of v to the power n. Okay, so this is true for all distribution functions, as long as our n random variables have identical distributions and they're independent. This is true. And because we're dealing with a uniform random variable, we know that this is equal to Vn. Okay, so let me rewrite this here, f1 v. For the uniform case, I now have the distribution function for our first order statistic. Okay, now to find the density function, I simply differentiate. So lowercase f evaluated at a point v is going to be the derivative of the distribution function with respect to v. V evaluated at that point. So this would be n times v to the power n minus 1. Okay. So now I've calculated, apologies, this should have an f1 of v. Okay, I can't quite fit it in. So this is the density function of our first order statistic. This is the distribution function for our first order statistic. So now let's put this to use. Let's let's calculate the expected value of our first order statistic. So remember the general definition of expected value. So what's the expected value of our first order statistic? The general definition is that you take the integral. In this case, it's between 0 and 1. It might be minus infinity up to positive infinity. You get the same answer. And then you multiply v by the density function. And then you vary v. Okay, so this is the general definition of expected value. You're taking each possible value, multiplying it by its likelihood or its density value, and then integrating over the whole interval. So we've seen that before in lecture 3 in the technical appendix. Now we can actually calculate this. So I know that this f of the density function of the first order statistic is this chap here. So let's replace that. This is 0, 1. I've got v multiplied by v to the power n minus 1. So I've got n times v to the power n dv. Okay. So this isn't too difficult to handle. I can take that integral and it's the reverse of differentiation. So I would say this is n divided by n plus 1 v to the power n plus 1. Just double check. If I differentiate this, I get this. Okay, that's good. And then, so I'm evaluating this notation here, putting large brackets with a 1 and a 0 means evaluate what's inside the brackets when v equals 1, and then evaluate what's inside the brackets when v is 0 and deduct the second from the first. Okay, now inside this bracket is clearly 0 when v is 0, and when v is 1, it's simply n over n plus 1. Okay, so there it is. That's the expected value of our first order statistic. It takes a very nice form. It's very easy to calculate. If I give myself an easy number, so for instance, if n is 19, then the expected value of the first order statistic would be 19 over 20, which is 0.95. Okay, so how nice is that? Essentially, we can why this is going to be useful is because you could imagine if we're running an auction and say 19 people walk into the room and we are assuming that they all have some value for the object that's being sold, but we don't know their values, they're private, so we make an assumption that, well, we'll treat them as a random variable and they're uniform on 0 to 1, for example. Well, then we know that the expected value of the individual with the highest of all of those values who've walked into the room would be 0.95. Now, we don't know how he's going to bid in the auction yet. That's going to depend on the rules of the particular game. But we are able to say something about the expected value of the highest of these random variables, which is going to be very useful.